In this video, we are going to do a very simple Nastran Solution 200 example. And by the end of the video, this is what we plan on doing. We have this rod subjected to an axial load with a set radius at the beginning. Our goal is to modify the radius of the cross section, and our objective is to minimize the weight while making sure that the axial stress is within the limit that we have here. So just to give you an overview of what we will be covering, I'll go over the optimization problem statement. This is basically a summary of what we're varying, what our objective is, and what our constraints are. I'll then walk you through the process that you need to use in order to convert a BDF file to Nastran Solution 200. This is when we set up the design variables, the objective, and the constraints. I will then perform the optimization, and then we're going to look at the results in the F06 file. And then here it should say the plotter or online plotter. We'll look at the structural results, and then at the very end, we will go ahead and update the finite element model with our new dimensions of the structure, if you will. Before I go on, if you are a professional engineer and would like more advanced training, if you have a general question on Nastran Solution 200, you're more than welcome to contact me at this email address, and I will get back to you. Also, if you are a student or a professional engineer and would like access to the Nastran Solution 200 web app, you can also contact me at this email address, and I will get back to you. Now let's go over the finite element model real quick. One end of the finite element model is fixed, while the opposing end has an axial load applied to it. So you can imagine for this example, the only stress we'll have is axial stress. And on the next slide, I just have a quick summary of the optimization problem statement. It's composed of 3 items. The first one being design variables. Your finite element model will be composed of various properties. It could be composed of a density for the material, Young's modulus, Poisson ratio. Here, the cross-section is defined as a circular cross-section, so one of the properties there is radius. This property is what we will be allowing to vary during the optimization. So here we're going to call the radius x1, and we're going to let the radius vary between 0.001 and 100. Now, in terms of our objective here on the right and our constraints, your finite element model will produce a lot of quantities. It can produce a single weight or volume quantity. Each load case will produce a set of displacements, strains, stresses, and so on and so on. It's up to you to decide what quantity you want to minimize or maximize for the objective. It's also up to you to select your design constraints from these outputs. Here on the right, I have our objective. Our objective, called R0, will be to minimize the weight. Our design constraints, R1, will be the axial stress of any element associated with P bar L1. Here you can see we have about 10 or 11 finite elements. P bar L1 is used to assign the cross-section and material to each individual element. When we take the axial stress constraint, each element will have its own axial stress. So here we are constraining the stress of about 10 or 11 elements here. The reason I'm not sure if it's 10 or 11, I just haven't counted. Also, we have a bound on the design constraint. R1, the axial stress, is to be no greater than 110 e to the 6. Now, let's go ahead and walk you through the procedure. The first step is to start off with a BDF or DAT file. This BDF or DAT file is something you may have already created in your pre-post processor. Here is my axially loaded rod, if you will. And here on my desktop is that same model that I've already exported. Here is just a summary of this entire finite element model. This file has to be converted to Nastran Solution 200. So now that you are at the starting point, we can then proceed to the next item in the list, which is converting this file. If you would like to follow along, there's a link to this PDF file in the video description below. If you would like access to the Nastran Solution 200 web app, you can also contact me at the email address I showed a moment ago, and I can get you access to that. So give me a moment while I go ahead and start the Nastran Solution 200 web app. Again, if you would like access to this web app, you can email me and I'll send you a personal link of your own that you can use. So here's the web app. The first thing we will go ahead and do is upload the BDF file I mentioned a moment ago. So we'll go ahead and upload that. The web app will identify all the properties that can be set as design variables. Remember, I said you could set the Young's modulus, the Poisson ratio, the density as design variables. But here what we want to do is find the property that corresponds to the radius of the cross-section. Here we're dealing with the P bar L1 entry, and dimension 1 is what corresponds to the radius. So let's go ahead and click on the plus icon, and the web app sets that property as a design variable called x1. Here in this table, I can specify my bounds for the design variable, and here we said we want the design variable to vary between 0.001 and 100. So let's go ahead and type in 100 here. Here on the right, you see the necessary Nastran entries for this design variable. These are created for you as you use the web app. They are immediately updated as you modify some of these input boxes. And a quick note, for the status, you want to make sure that the status is always this blue checkbox or check mark. If you see something like this as an example, you'll get an error saying that these entries have not been properly configured. So your goal is to avoid this situation whenever possible and obtain this blue checkbox. Now, moving on to the objective, this is simply setting the weight. Here you can see that since we're dealing with the stress analysis, there are a lot of quantities you can set as an objective. But here we want to set the weight and we want to minimize the objective as much as possible. Now for the constraints. Here again, you have this long list. It's up to you to really pick what you want. And then this is where I would like to emphasize the importance of your optimization problem statement. It's very important you have this clearly defined so when you use the web app, this is a little easier on you. So let's go ahead and select the stress. And we'll go ahead and apply the stress constraint to any element associated with P bar L1. And then there are a lot of stress quantities you might get from the elements. Here we're focused on the axial stress. So we'll select the 6th item in the list. And then here we said that we want the upper limit to be 110 E6. And now let's go ahead and quickly jump over to the exporter. So here we have our case control section here on the left. So if I open the BDF file that we started off with, here the web app has gone ahead and converted it from a solution 101 to solution 200. It's also added a few other parameters that you need to perform optimization. Although not shown is the bulk data section, this is hidden for now. If we go ahead and download this, and let me go ahead and do that now for you, and we open that up, this file, the model PDF file I just downloaded, is the converted solution 200 file with the entire finite element model here defined. I also have to download the second design model file. You can see here I have the properties or the bulk data entries for the design variables, the objective, and the constraints here. So this is all necessary for the optimization. Let's go ahead and download this too. And both of these files have been downloaded to my downloads directory. So now let's start Nastran, select the model BDF file, and click run so the optimization occurs. Now, one thing you want to do after optimization is complete, you want to inspect the F06 file. At the very end of this file is a status message, if you will. This will indicate if your optimization went through successfully. And here I scroll to the very bottom. If you scroll up just a little bit, you see this table. This one's called a summary of design cycle history. Right after this table, so this would be the entire table, there's this message here that says run terminated due to hard convergence at an optimum. This is an indication that your optimization went through successfully, which is good for us because this means we set this problem up correctly. Now let's go ahead and look at a few details here. Let me go to the online plotter. During the optimization process, a number of files have been created. One of them is this comma separated value file. Here I can go ahead and select that CSV file and upload it, and I can view the results of my optimization. Remember, our objective was to minimize the weight. So these values that you see for the objective is the weight. Here I have 5.3 units of weight at the beginning, and then towards the end of the optimization for my final design, I had 2.46 units of weight. Here are my design variables. We only had one design variable called x1. So here the radius started at 0.025 units of length. And then at the very end, we have an optimum radius of 0.017 units of length. Now, that's how you perform and set up your optimization. Let me go back to the agenda, or rather, let me go ahead and go through this process here. Let's look at the structural results. It's always important to look at your results just to make sure everything looks okay. So here what you can do is attach the result file. Here a new XDB or result file was created. For you it might be different. It might be an OP2 file. It might be a master DBL file. What's important here is that you go to analysis, click on XDB, and select this result file. So let me go ahead and navigate to that file and import it to my database here in Patron. Now let's go ahead and look at the results. I want to look at the stress results, so let me go ahead and set that up. And one thing you'll notice here is that we have two sets of results rather. The first set of results is labeled D0, and you can see that very small here on the right hand side of the screen. The D0 represents the initial design of your finite element model. So here on the far left hand side, this is the starting point. This is your original model, and these quantities that you see here on the screen now for axial stress, these are the original stresses for this model. The second set of results corresponds to D3. D3, if you see here, is D1, D2, and D3. The final design cycle is known as D3 in this example. So here, the second set of results corresponds to the structural results of the optimized model. So now let's go ahead and plot these stress results. You can see that if we look at the before results, we have a stress about 50 E6. Our new stresses are about 110 E6. So the optimizer has minimized the radius until one of the stress constraints was violated, and that's what happened here. So there's one last thing I want to do before we call this tutorial complete, and that is update the original model. Let's go ahead and minimize this. Here on the left is my original PDF file. Again, it's in the description of the entire model. There's this entry called P bar L1. This entry is what contains the definition for the radius of 0.025. This is what we now have to change in order for this finite element model to be updated. What we can do is create a copy here on my desktop. And then here, I'll leave it as copy. And I'll open this here in Notepad. In your directory where you perform your optimization, there's a new PCH file. Let's go ahead and open that. This file contains updated properties for the properties you varied during your optimization. Here, you can see there is a P bar L1 entry. Instead of seeing a radius of 0.025, you see the optimized radius, which is 0.017. This is the same value that we found here in the plotter. Here we started off at 0.025 and we ended off at 0.017. So now what I can do is copy this entire entry. So here, let me move this to the right. I'll copy this entry from the left here, and then I'll paste it here on the right and replace the old p bar L entry. So there we go. Let me go ahead and save this file on the right. And now our radius here, instead of being 0.025, is 0.017, which is the optimum property. So this file that's on the right has been updated with the optimized radius, and I can hand this off to another engineer or classmate if you're working on a project. So there you have it. That is how easy it is to perform an optimization with Nastran. Again, if you are a professional engineer and you would like more advanced training, if you have a question on Nastran Solution 200, my email address is here in the middle of the screen. Feel free to send me a note. If you're a student or a professional engineer and would like access to the Nastran Solution 200 web app, you can also contact me at this email address, and I would be more than glad to work with you. As always, thank you for watching, and if you have any questions, here's my email, or you can leave me a comment in the video comment section below.